Okay, let me find the first slide here. There we go. All right. Chemistry 3111, Organic Chemistry 2. This is Chapter 21, Alpha Carbon Chemistry, which largely deals with enols and enolates. And so if you don't remember what an enol is, we're going to talk about that, and we'll talk about what an enolate is as well. But you can imagine if it ends with 8 in chemistry, it's usually something that has a negative charge. Well, let's talk about this whole alpha carbon thing first. Alpha is a Greek letter. It's the first letter in the Greek alphabet. So Greek letters are used to describe the proximity of carbons relative to the carbonyl group in a ketone that's shown here, or it could be an aldehyde. And so the carbonyl carbon does not get a Greek letter assigned to it. It is not special. But once you start branching out from there, we give Greek letters. And I don't have the whole Greek alphabet memorized, but I do know that it goes from alpha to beta to gamma and then to delta like that. Now, we're not going to be looking at anything past delta. In fact, we're not going to be looking at anything past alpha because this chapter deals with reactions that take place at the alpha carbon. And so we're going to be concerned with the alpha carbon, which would be, this carbon, should be this here and this carbon here. So this ketone has 2 alpha carbons. Of course, if we have an aldehyde, we would have only 1 alpha carbon. And let me explain what I mean by that, right? If we were to draw a generic structure, I don't know, let's draw propionaldehyde, so we'll put our hydrogen here. Okay, so we have 1, 2, 3 like that. So there's propionaldehyde. Well, this is the alpha carbon right here. Okay, and on this side, there's no alpha carbon. So no alpha carbon. Okay, so an aldehyde, the side that has the hydrogen obviously has no alpha carbon. All right, well, enols and enolates, let's get into that a little bit more. This is the alpha protons, or the protons attached to that alpha carbon. So if we go back a slide and we analyze this ketone and this aldehyde, let me just choose my black pen here, right? We know that there are 2 protons here, right? We know bond line structures, and we don't include those, but we know that they're there, right? And we know that there are 2 alpha protons here as well. And so what it's saying here on this slide is that alpha protons, or those protons attached to the alpha carbon, good enough. And those protons are relatively acidic, okay? Now, compared to what? Well, we're going to talk about that. But you can see that we can remove one of those alpha protons and we can form what's called an enol or an enolate. And it's actually not removal of the proton to form the enol. That's a tautomer. But anyhow, most reactions that are going to be covered in this chapter proceed via an enol or an enolate intermediate. And if you're wondering where the word enol comes from, well, you can probably guess that it comes from, right? We have an alkene, okay? So we have the ene, and then we have an alcohol attached to the same carbon. And so that's where we get the name enol, okay? But if we take a strong base, okay, we know that there are 6 alpha hydrogens in acetone, which is propanone. If we take a strong base, let's say, strong base, okay, and we deprotonate like this, okay, we can end up forming an enolate, okay, and then that enolate could act as a nucleophile, and, we could draw something like this where, these electrons could act as a nucleophile, and we could put a substituent in place of that alpha carbon. Now, we could also draw a mechanism from the enol, and we will look at that, how we can add something to the alpha carbon of an enol as well. So enolate, negative charge, enol. Okay, so this is kind of the take-home message from the slide. You need to know what an enol is. So this is an enol, and then an enolate. So an enolate. And I'll be honest with you, this chapter is largely going to deal with enolates. Okay, we're going to talk about those quite a bit more than we will enols, but at the beginning we will talk about enols. So here we go, a little bit more about enols. If we take a ketone or an aldehyde and we put it in the presence of an acid or a base, the ketone or aldehyde is going to exist in equilibrium with the enol. So again, ketone and enol forms are what we call tautomers of one another. Okay, these are not resonance structures at all. Tautomers are simply constitutional isomers that differ in the placement of a pi bond and a hydrogen, right? You can see that this pi bond, okay, this double bond moved here, and then there was a hydrogen here that ended up moving, over here, okay? So that's what the definition of a tautomer is. And if you look at the case of cyclohexanone, which is the 6-membered ring with the double bond to an oxygen on it, the carbonyl, you see that it is in equilibrium with its enol form, okay? So this is what we call the keto form, and this is what we call the enol form. Well, they are in equilibrium, but you can see that there's a lot less of the enol, right? Less than 0.01%, and most of it is, in fact, the ketone. All right, but you might be wondering, are there cases where the enol would predominate? And the answer is yes, and we're going to look at 2 specific examples where the enol form would predominate over the keto form. And here we see there are exceptions, and here's one of them. When we have a 1,3-diketone, and that's what's shown here, and the reason we call that a 1,3-diketone, you can imagine, is because the 2 carbonyls are, 1, 2, 3 carbons apart, so that's a 1,3-diketone. And if we look at the equilibrium here, you can see the equilibrium actually lies of what? This is the enol here. Okay, this is our enol, and again, the equilibrium on the top is telling us that the equilibrium lies mostly to the side, and it's also expressed by these percentages that we have, between 70 and 90% of the enol form, and there's a 2-fold reason as to why the enol form predominates. Now, you can probably guess one of them right away, which would be the hydrogen bond, okay, because we know that the hydrogen is delta plus in an oxygen-hydrogen bond, and we know that the carbonyl oxygen is delta minus, right? We know it's more electronegative than carbon, and so that's a polar bond. And therefore, we're going to have that hydrogen bond between the lone pair on the carbonyl and the hydrogen of the hydroxyl of the enol. So that's one reason. But the other reason is because it's stabilized by conjugation, right? Conjugation. Now, what's conjugation? Now, that's something that we've covered several times, but I'll remind you that conjugation is when you have double and single bonds alternating. And we know that there's an inherent stabilization effect due to conjugation. So you can see we go double, single, and double bond like that. So that's the conjugated system. So again, 2-fold reason as to why in this specific case with this 1,3-diketone that the enol form predominates over the diketo form. Okay, well, there's another example, and I bet you can guess why this one, is the way it is. Okay, if we look at phenol, everybody in the class knows what phenol is. It's one of those aromatic compounds that I asked you to memorize its common name a long time ago. The phenol is an example where the enol is vastly favored over the keto equilibrium, right? You can see that we have, right, if you just zoom in on this spot right here, there's an enol right there. Okay, why? Because this carbon possesses both an alkene and an alcohol on it. But you can see that the phenol exists, more than 99.99% of the time versus the keto form. Okay, so again, this is the keto form and the enol form. And the reason why is based off of what? Aromaticity. We spend a lot of time talking about aromaticity and how aromatic compounds have increased stability. And we covered that in gross detail earlier on in this course, so I'm not going to rehash all of that. But there's this very good example of an enol predominating over a keto form. So 2 specific examples, and you should be aware of those. Well, let's talk about some mechanisms here. The mechanism of tautomerization, which again is just an isomerization, right? If you look at the keto and the enol tautomers, they are nothing more than constitutional isomers. They have the same molecular formula. How do they differ? They differ in the connectivity of the atoms. And in a tautomer specifically, they differ in the placement of a pi bond and a hydrogen. Now, what is the mechanism for that tautomerization? Well, it depends on whether it's acid catalyzed or whether it's base catalyzed. And this is the mechanism for the acid catalyzed tautomerization of a ketone. Now, this specific ketone, this is acetone. It's acetone that's shown here. So the first step is protonation of the carbonyl group, and then we have a resonance stabilized cation. Okay, and when we draw this resonance contributor right here, we can show water coming in, since water is the conjugate base of hydronium and acting as a base and deprotonating that cation in order to produce the enol. You need to know this mechanism, okay? This is a very important mechanism in organic chemistry. Tautomerization of a ketone to an enol. And in basic conditions, I bet you could draw this one, without me even showing you, right? Because we talked about how the alpha protons are, I said they're relatively acidic. Now, relative is a term that you'd have to look at the quantitative aspect in terms of the pKa, and we're going to do that soon enough. But if you have hydroxide, which is a strong base, it's strong enough to deprotonate at the alpha position and produce that resonance stabilized anion that we call what? It's got a sassy name, right? This is called an enolate. And then we can protonate that enolate because water is the conjugate acid of hydroxide, so it can donate a proton to the oxygen, and we end up producing the enol. And again, this is another mechanism that you have to know. You want to know the base catalyzed tautomerization of a ketone to an enol. Very important mechanisms in organic chemistry, and we're going to see them over and over and over. Now, if you have a ketone or aldehyde, we talked about at the beginning, I said, well, if you have, a ketone, the keto form and the enol form, you have very little of the enol form. Well, let's look at this slide here and see what it has to say. It's safe to assume that some fraction of a ketone or aldehyde in solution is going to exist in the enol form. In fact, this is really interesting. This electrostatic potential map of, this is the enol of acetone. Okay, so this is the electrostatic potential map of this compound. Now you can see we have two resonance contributors, right? And we can draw a resonance contributor where we have a negative charge on a carbon, right? So we have a carbanion there. But we know that in this one on the left, right, the oxygen is more electronegative, so it should pull more electron density towards itself. Now remember, these are resonance structures, okay? These are just ways that we describe the overall molecule, right? It's not vibrating in between either of these. I always have students, not always, but sometimes I'll have students saying, oh, it's vibrating between, the resonance structures. No, not at all. Resonance structures are a way to explain the hybrid, right? The way to explain the overall placement of electrons in the molecule. And so when you look at that electrostatic potential map, where the molecule is red, that means that there's more electron density. And look at this. You can see that we have a lot of electron density up by the oxygen. Makes sense. It's more electronegative. But look at this. There's some red on this side, okay, by this carbon. And that tells us that, that carbon is electron rich, okay? And that's going to be important, or an important concept to keep in the back of your mind moving forward, that carbon is electron rich in that enol. In fact, that'll help you understand some of the mechanisms that we're going to look at today. All right, in the presence of a strong base, we form an enolate. In fact, I drew this mechanism for you earlier. I drew this step here, but I didn't draw the resonance stabilization. So I didn't draw, these two curved arrows right here. But you can see that when we do the deprotonation, that we have resonance stabilization in that enolate. Now, the enolate is much more nucleophilic than the enol. Why? Well, that makes sense, right? Because it ends with 8 and it's got an overall negative charge, right? And that's the arrow that I drew earlier on. I said, well, you can see how it can behave as a nucleophile like that. All right. Well, and if you're like, well, that's kind of just quick, Mr. Dan, don't worry. We're going to talk about it more. We're going to see enolates behaving as nucleophiles, almost Avogadro's number of times throughout this chapter. Now, you might be asking a question, which is, why are you drawing two arrows like that to draw a nucleophilic attack? Isn't the oxygen negative? Can't that be a nucleophile? The answer is yeah, sure it can be a nucleophile, absolutely. And that is summarized on this slide. Okay, the enolate can in fact undergo carbon attack, which is the first mechanism I drew, or it can undergo oxygen attack, okay, which is what I just drew last, okay? Now, enolates generally are going to undergo carbon attack, which is drawn one of two ways. You can draw it in two steps, and that's how I drew it on the previous slide, or you can just draw the negative charge on the carbon and draw it like that. That's no problem. The reason why, and you probably have this figured out already, but the reason why I draw this one is if you think about the two resonance contributors, this versus this, which one of them is going to be the major contributor? Well, it's going to be the one where the negative charge is on the oxygen. So since that is the predominant resonance contributor, that's how I like to draw it. Can we draw the mechanism, like this? Absolutely. In fact, the book does it many, 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 many times. Okay. So either one is completely acceptable. Okay. Now, just a little bit more about the oxygen attack. If you're the kind of person that likes to research things on the internet, you can look up oxygen attack and when that is preferred and the conditions for that. But most of the, in fact, all of the reactions that we're going to look at in this chapter involve the enolate behaving as a nucleophile from the carbon. Okay, we're not going to look at any O attack at all in this chapter, and there are good reasons for that. I'm not going to go into it right now, but yeah, we'll just leave it at that and move on. Okay, so alpha protons are the only acidic protons on an aldehyde or a ketone that can be removed to form an enolate. Now, the reason we're not going to remove beta protons is because we wouldn't end up with a resonance stabilized intermediate, right? If I pull off, let me just kind of draw an arrow like this. If I take a strong base, right, and we're going to look at this several times. Let me pick the green pen here for a second. If I use a strong base and I deprotonate like this, let me draw, maybe I could spice up that arrow, spruce it up, right? Okay, if I draw what I get from that, let's just draw what we'd end up with. So we're going to have our carbonyl. We've got 1, 2, 3 more carbons like that. Okay, this hydrogen is still going to be here. Draw the other one like this, right? But we're also going to have a negative charge, right, on that carbon. Now you know that that's resonance stabilized, right? And I can draw that resonance contributor, right? So I can delocalize those electrons, and I can draw the resonance contributor, which looks like this, and this is the enolate. Okay, they're both enolates, but I find it easier, to think about it like this. So there we go. So those are the two resonance contributors. Of course, that hydrogen that I had in red, it's still there. If I was to remove either of those two protons or either of these three protons on this methyl, I can't draw a resonance stabilized intermediate. Okay, impossible. You don't believe me? Try it. Okay, and you'll see that you cannot draw a resonance stabilized intermediate. Now the question becomes, what kind of base are we going to use? Right? You're just saying, oh, Mr. Dion, you're just throwing bases at it and you're deprotonating it. Well, in fact, our choice of base is going to be important throughout this chapter. So let's take a harder look at the kind of bases that we would use. And before we do that, let's talk about the pKa's of these alpha protons. The pKa of an alpha proton, of course, we have to consider that when we're choosing an appropriate base, right? If I were to treat, any one of these, ketones or aldehydes, if I was to treat these with a base that's not going to fully deprotonate it, well, then I only get partial deprotonation. If I treat it with a really strong base, I'm going to get complete deprotonation. So the pKa of a ketone is around 19. Sorry, I can hardly see here, but it's around, 19 for acetone, 18 for acetophenone. So close enough, high teens. And acetaldehyde or ethanol has a pKa of around 17. Okay, so here we have the pKa, so you should know they're kind of in the high teens. That's going to be close enough. What's the range here? Around 17 to 19, right? That would be good enough to get you where you want to go in this chapter. Okay, so we'll say in the neighborhood of 17 to 19 for our pKa's for our aldehydes or ketones. All right. Okay, well, how are we going to use that, in terms of the kind of bases that we want to use to form enolates? Well, what if I chose ethoxide, right? This is a real chestnut in this class, right? Sodium ethoxide, we've used it Avogadro's number of times, right? NaOET, right? We always write that down. Sodium ethoxide is a great base. We've done, elimination reactions with that to form alkenes. But what if I took sodium ethoxide? Now the spectator ion is left out, the sodium's left out. Well, what if I took ethoxide and I treated that with, or took ethanol and I treated that with ethoxide? Okay, what's going to happen? Well, the pK of acetaldehyde or ethanol is 16.7, and the pK of the conjugate acid of ethoxide, which is ethanol, is 16. I mean, that's way too close, right? And the equilibrium is going to lie on the side of the weaker acid. So in fact, we have an equilibrium here, which is going to lie to this side, right? It's going to lie to that side. And what's important here is that when the pKa values of the base and the enolate are similar, or you could say the pKa of the conjugate acid of the base and the pKa of the aldehyde or ketone, when they're similar, we're going to have both reactants and products in significant amounts. Now you might think, okay, well that's useless. No, it's actually useful depending on the situation. When the alkoxide is used, the enolate nucleophile can react with the ketone electrophile, and we're going to look at that in a second. So what it's saying is this, okay? And we're going to look at this in great detail later on in the class. But think about it. If I take a whole bucket full, Avogadro's number of molecules of this, and I treat it with ethoxide, what am I actually going to have? Because I have an equilibrium, that means I'm going to have some of this, and I'm also still going to have some of this, right? Which is just this. I just redrew it. Okay, that means I'm going to have both of these species in the solution. We'll hold the phone because now I've got a nucleophile, right? This is a nucleophile right here. And I've also got an electrophile, right? We know this is delta minus and this is delta plus. So if I erase all that spinach, what it's saying in the second bullet point is this, is that if you treat the aldehyde or ketone with ethoxide and you have both of these species in solution, that means that you could get this kind of reaction occurring where this acts as a nucleophile. Okay, cool, huh? Okay, and then again, that's going to be covered in detail in another section. Now let's talk a little bit more about some different bases that you could use to deprotonate an aldehyde or a ketone to form an enolate. If you completely want to form the enolate, you don't want any of the enol, you could use a strong base like sodium hydride, right? The benefit that you have there is that you form hydrogen gas, right? When the hydride takes a proton, you get H2 gas. Now the pKa of H2 gas, pKa, is around 35, okay? And you could write that, in fact, why don't we just move that? Why don't we just put that over here, and we'll draw H2 over here. And the pKa of acetaldehyde was what, 16.7? So you can see that the equilibrium, if it's going to lie to the side of the weaker acid, heck yeah, it's going to lie to the side of the products. And you also take advantage of Le Chatelier's principle, because as hydrogen gas is lost from the reaction, as it bubbles out of the reaction mixture, because it's a gas, right? It's going to push the reaction towards the product, the enolate. Okay, so that's one way. There's another way. This is a new base. So I'm going to introduce you to a new reagent today. If you look at the reagent sheet for chapter 21, it's going to have something. It's just going to say LDA. And LDA stands for lithium diisopropyl amine. So that's LDA. And LDA is a strong base commonly used to form enolates irreversibly. It's made by treating diisopropylamine. So that's an amine. This is a secondary amine with two isopropyl groups on it. And you treat it with N-butylithium, right? So N-butylithium, we abbreviate that N-buty like that. Now, butylithium is a really strong base because the conjugate acid of butylithium is butane, which is a pK of 50, right? Around 50. So the equilibrium, you can see, is going to lie hard to this side because the pK of the amine, the pK of an amine is around what, 35? In the book, it says it's 36. Okay, so we have a difference of 14 pKa units, and so the equilibrium will lie hard to the side. So what am I saying? If you want to have LDA, I mean, in this class, you're just going to be able to write LDA over your reaction arrow and, go home. Everything's good, okay? But in reality, if you purchase LDA, and I've bought it a few times in my life, it's actually not the greatest thing to buy from a chemical supplier. And the reason why is it's extremely hygroscopic, meaning that it absorbs moisture from the air, and that will just ruin it. You get, you just end up producing the amine. So usually if you want LDA in a reaction, you actually make it on the spot. And so the way you do that is you would distill some diisopropylamine to make sure it's very pure, and then you would treat that with some N-butylithium, right? And you would deprotonate that, and you end up with your LDA. And then you have butane, which is a gas, and that's going to leave the reaction mixture. Why? Because butane is a gas, right? Okay, so you actually kind of make it on the spot. usually when you need it. If you're, my personal experience, and maybe you don't want to hear about this, but every time I've bought LDA in a bottle, it's good for about one use, and then as soon as you stick a needle in it, something, it seems to deteriorate pretty quickly. Now, if we take that aldehyde, and this is the ubiquitous acetaldehyde that keeps showing up here, right? This is acetaldehyde. When we take that and we treat it with, this is LDA, we end up forming the enolate completely, right? This is complete deprotonation. Why? It's based off of the difference in pKa. Remember, the equilibrium is always going to lie to the side of the weaker acid. Here we have a difference of almost 20 pKa units, 10 to the power of 20. And so when LDA is used to form the enolate, the amount of ketone present at equilibrium is negligible. You can just forget about it. LDA has these two bulky isopropyl groups. This is an isopropyl group. That's an isopropyl group, which allows it to be a good base, but it's going to be a terrible nucleophile. Why? Because it's just, frankly, it's too sterically hindered. Nothing more than that. Okay, so brand new base, LDA. And that is used when we want complete total deprotonation. Same thing with sodium hydride. But if we only want partial deprotonation, and again, we will look at cases where that's what we're going to want, then it will be the appropriate base. And I have a table that summarizes that in a few minutes. Now, let's just talk about one more scenario before we get into looking at the table of what base to use at what time, okay? And then we'll try some practice problems. If you've got this 1,3-diketone, and we looked at a 1,3-diketone earlier on, the alpha protons that are in between the two carbonyl groups, so these guys right here, not these ones, okay? These ones are still going to have a pKa of around 19. But if you look at those two protons that are sandwiched in between the two carbonyls, those are really acidic, right? They have a much lower pKa than, say, acetone. Okay, 10 log units more acidic. Why? Because when you deprotonate that, you end up with a doubly resonance stabilized enolate. Okay, so if you were to remove one of these protons, and you should be able to draw, if I was to take a strong base, and if I was to remove this proton like that, what would I get? I'd end up getting this structure with the negative charge on the carbon, and I can draw that negative charge being delocalized up on this oxygen or on the other side. So the increased acidity is due to the increased stability of the resulting enolate. Think all the way back to the basis chapter in Organic Chemistry 1. What makes something a good proton donor? What makes something a strong acid? It's the stability of the conjugate base. So since we have a more stable conjugate base, we have more acidic protons, okay? Or protons with greater acidity, I should say. And that begs the question, what would happen if we were to take that, 1,3-dicarbonyl, and we treated that with ethoxide, right? And we're kind of going back to the beginning, right? We started out by talking about sodium ethoxide. Well, what if, right? Well, this is a kind of an interesting scenario, because if I took ethoxide and I treated it with just a regular aldehyde or a ketone, I ended up with some deprotonation. But if I treat a 1,3-dicarbonyl with sodium ethoxide, look at the difference in pKa. Here's the pKa of my acid, and here's the pKa of the conjugate acid of ethoxide. Well, that's a difference of what? 7 log units. And so 1,3-dicarbonyls are acidic enough to be irreversibly deprotonated by an alkoxide. So this is a scenario where the alkoxide would be sufficient. In fact, there's no need. It says right here, there's no need to use sodium hydride or LDA to form the enolate because it's overkill, right? Not necessary to pull out some kind of strong base like that. Now, that's quite a bit of talk about acidic protons and bases this morning. So it would be a good idea for you to familiarize yourself. And familiarize what's that? That's the instructor's politically correct word for memorize, right? It's a good idea to familiarize yourself with what base should be used in order to generate an enolate depending on the carbonyl compound in the desired result. Okay, so there's 3 scenarios here. If we have a ketone or aldehyde, and if we want to do, partial deprotonation, okay? So this is a reversible process. We're going to treat it with something like sodium hydroxide or sodium ethoxide or sodium methoxide, okay? And then we're going to end up with both the enolate and the ketone in solution. Now, again, if you're wondering, like, what the heck is that good for? Well, we're going to look at that, okay? But I told you that you're going to have a nucleophile and an electrophile in the same solution, okay? And again, we're going to look at that in more detail. If you want to deprotonate that ketone or aldehyde completely, well, in that case, you would choose either sodium hydride or lithium diisopropyl amide, okay, LDA. All right. Again, that's irreversible. And if you have a 1,3-dicarbonyl, so the 1,3-dicarbonyl, you just need to use an alkoxide or a hydroxide base, and you're going to get almost complete deprotonation. And so LDA or sodium hydride, not necessary there, okay? So again, it's a good idea for you to memorize, these scenarios. But what would be an easier way, or a more, maybe not easier, but a more effective way to know this, rather than just sitting down and meditating on it or something, would be to practice, right? Because the more you expose yourself to these 3 scenarios, the more logical they will become, okay? And, something I told you a long time ago, and this is for most of you who took Organic Chemistry 1 with me, and, if you remember way back to the acid-base chapter, right? I told you earlier on that if you memorize all those pKa's that we looked at, and because the pKa tables that we looked at obviously are not exhaustive. I don't have an exhaustive knowledge of all pKa's, pretty good knowledge, but the more pKa's you have memorized, the easier this kind of thing becomes, okay? Gets much easier to rationalize what the heck is going on here. I remember when I first got into industry, I worked with a guy who just had an incredible knowledge of pKa's. I said, we were talking about something to do with amino acids, and I had an amino acid that I was reacting on this big compound, and I said, I don't know what would the pKa of this proton be? I had a guess, and this guy was like, he just 21. I said, how did you know that? And he said, oh, my supervisor in graduate school was so big on us memorizing every pKa under the sun that I have them all memorized, man. And I was like, yeah, it's not a bad idea. Anyhow, let's try a question. This is question 21.6 from our textbook. It's just asking us to draw the enolate ion that's formed when each of the following compounds is treated with our old favorite sodium methoxide, right? You guys know what sodium methoxide is. That's NaOET, sodium methoxide. In each case, draw all the resonance structures of the enolate ion and predict whether a substantial amount of starting ketone will be present together with the enolate equilibrium. Jeepers, you could ask more questions maybe. Yeah, there's a lot of questions in here. Well, let's start with the first one, B. And what do I notice here? I mean, the first thing that I notice is I have 2 axes of symmetry, right? I have an axis of symmetry going this way, and I have an axis of symmetry going that way. So that means, based off of those 2 axes of symmetry, that I really only have 2 distinct alpha protons, right? These are always alpha protons. So this is the alpha carbon. But I could have drawn these 2 in, right? Because these 2 protons are alpha to this carbonyl. Anyhow, I'll just start with those 2. And if you're thinking, well, hold on, man, doesn't that have 2 carbonyls? Yes, but it's not a 1,3-dicarbonyl. This is a 1,4-dicarbonyl, right? 1, 2, 3, 4. So we could put that in here. Not a 1,3-dicarbonyl. So don't fall into that trap. So all that information that I just presented about 1,3-dicarbonyls is irrelevant here. Okay, it's not a 1,3-dicarbonyl. Now, if we were to take our sodium ethoxide, okay, we know the pKa of the alpha proton of a ketone is going to be around 19-ish. Okay, somewhere between 17 and 19. I don't even know this one exactly. We'll say, I don't know, let's just say for interest sake, it's around 17. Okay. Anyhow, if we take our ethoxide, and again, I'm going to leave the spectator ion out. If we draw our ethoxide, let's draw the deprotonation. So we're going to end up ripping off one of these protons, and we're going to have a negative charge on our carbon. Let's draw that out. It's going to look something like this. We have 1 carbonyl intact here. We have the negative charge on our carbon, like that. The other proton is still there. Okay, this proton is still here. I'm going to leave it out, and we should now draw the resonance structure, right? So let's draw that out. So we have resonance stabilization here, comme ça, as we say in French. Okay, and let's draw that enolate ion. So we'll put our negative charge up on the oxygen like that. Now, not only do we produce the enolate, and this is showing the resonance stabilization of that enolate, but we're also going to produce ethanol. Okay, we're also going to produce ethanol. And if we back up a few slides, you see that the pK of ethanol is 15.9. So let's write that in. We'll just say 16. Okay, just to make things simple, we'll say pKa, we'll just keep 2 sig figs, is around 16. Now, the equilibrium is supposed to lie to the side of the weaker acid. Is that a big enough difference in pKa that the enolate is going to predominate? The answer is absolutely not. Okay, and so we'll just write here, let's just keep it simple. I'm looking at my notes here, cheating. We'll just say both exist. Okay, so we're going to say both ketone and enolate exist at equilibrium. There's my shorthand for equilibrium. Okay, so give me a thumbs up if you follow me on that one. Just give me a thumbs up if you're like, yeah, I think I follow that one. And we can move on. Good, thanks, Sean. All right, thank you, Kylie, David, Kyer. Perfect, excellent. Well, let's try the next one. The next one is an interesting scenario because, let me just ask you a question. Are there any alpha protons on the left side of that carbonyl where I have a circle? Are there any protons attached to that carbon? Any alpha protons on this side, right? And the answer is a big old no, right? Absolutely there aren't. So this is a scenario where I literally only have one stinking alpha proton, and it's this one right here. So let's draw our ethoxide. Okay, this time I'll draw bond line structure like that, right? That's the same thing as ethoxide. I'll draw the deprotonation, so we'll do that. Oops, there we go. And let's draw the negative charge on the carbon, put in my aromatic ring first. There we go. Put in my carbonyl. Okay, like that. Oops, that bond's kind of ugly. There we go. And we'll put our negative charge like that. Well, we know that there is a resonance contributor because these electrons can be delocalized like this. And let's draw that resonance contributor that results from the delocalization of those electrons. And it's going to look something like this. Okay, like that. And there are no other resonance contributors here. So we're also going to end up with ethanol. And again, based off of the pKa, right? Since we just have a ketone and the pKa, let's say it's around 17 to 19, whatever. Anyhow, it's 17, and then the pKa here is 16-ish. So both are going to exist. Okay, both the ketone and the enolate are going to exist at equilibrium. So I'll just copy that, copy, and paste it down here. Okay, like that. Okay, if you want to look at an example where both are not going to exist, you'd have to move on to question, which one is it? A. So look at question A, and I ask you to take a look at that one. I think it's one of the questions that I've assigned. Question A. So make sure you look at that one. And that one, I'll just show you quickly. It's where you start with a 1,3 dicarbonyl. Okay, so you have a 1,3 dicarbonyl, and obviously if you treat that with sodium ethoxide, okay, and I'm kind of going over it quickly here, the equilibrium is going to lie hard to this side. Okay, oops, that bond's kind of ugly. And the reason why is because if we compare the pKa here, right, the pKa of the 1,3 dicarbonyl was around 9, and the pKa of ethanol is around 16. So the equilibrium is going to lie to the side of the products. Okay. Anyhow, I asked you to look at it, and then I do the whole thing. Whatever. Anyhow, let's talk about some reactions. What do you say? That covers section 21.1. Let's get into section 21.2. The students always like to talk about reactions. Ways to functionalize a compound. Well, if you take a ketone and you treat it under acidic conditions, and you can see that the acid is present in a catalytic amount. That's what those square brackets mean. You can take a ketone or aldehyde and convert it to an alpha halo ketone or aldehyde. So it undergoes what's called alpha halogenation, right? We have our alpha carbon, and then it's got a halogen on it when we treat it with an acid catalyst. and bromine. Instead of just using bromine, you could also use chlorine or iodine. You can't use fluorine, it's too reactive. But acidic conditions tells us that an enol is the reactive intermediate. And we already looked at the mechanism of the tautomerization of a ketone or aldehyde under acidic conditions. So the first part of this mechanism is going to involve the tautomerization. So again, the enol formation where it says part 1, you've covered this, right? We did that in gross and dirty detail. Well, looky, if you take that enol that's produced, right, this enol right here, here's my enol. As I mentioned earlier, that can behave as a nucleophile. It's not going to be as nucleophilic as an enolate, but it can still behave as a nucleophile. And so that's the first step that's shown here. It's reacting as a nucleophile towards what? Towards bromine. Okay? And then we end up doing a proton transfer with the conjugate base of hydronium, right? Which is water. We started it with hydronium. And so you notice that you end up producing, not only do you produce this alpha bromoketone, but you also end up making more hydronium, right? In this step, look, water is taking a proton, and that's going to give you hydronium. So this is what we call an autocatalytic reaction because it reproduces the acid catalyst, and you also have, bromide in here as well. Anyhow, kind of a neat reaction, and that's, again, I'm rehashing myself, but that's why you only need a catalytic amount of the acid, so an autocatalytic reaction. Well, you might be wondering about regioselectivity. What if I have an unsymmetrical ketone? And that's addressed here, and it's a very short explanation. If we have an unsymmetrical ketone, like this ketone right here, so this is what? 2-methylcyclohexanone. If we take that unsymmetrical ketone and we treat it with these conditions, so acid catalyst to form the enol, and then that enol can act as a nucleophile, right, on bromine, you see that we can end up with 2 regioisomers where we have the bromine, the alpha bromo on one side where it's on the more hindered carbon, and then we have the alpha halogenation on the less hindered, right? So this is more hindered, and then less hindered over here. Okay, and the reason why it's going to be on the more hindered carbon is because the more substituted the enol is, the intermediate, okay, it's going to be the more stable enol, right? And we looked at substitution of alkenes a long time ago. That's something that I think we looked at it way back in chapter 7 or something. Okay, we said the more substitution that we have on an alkene, the more stable it is. In fact, that's how we rationalized Zaitsev product formation over Hoffman product formation and things of that ilk. Okay, so that's our first new reaction. Okay, reaction number 1 is the treatment of an aldehyde or ketone, something with alpha protons, and we treat it with a catalytic amount of acid and bromine, and we get alpha halogenation, and then we just looked at the regiochemical considerations of that reaction. Well, if you're wondering, what the heck can I do with that alpha halo intermediate? Well, alpha halogenation provides a 2-step synthesis of an alpha beta unsaturated ketone. This is an alpha beta unsaturated ketone right here. You know what unsaturation is, right? A double bond or a ring. And so we have our alpha carbon here and our beta carbon. So that's alpha beta unsaturated because there's a double bond between the alpha and beta carbon. Now, how is this formed? Well, you're simply eliminating bromine using a base in the second step. Okay, so you end up forming, there's not a lot of space here, but in the first step, you end up forming this compound, which we already looked at. Okay, you end up with the alpha bromo ketone like that, and then in the second step, you treat it with a base like pyridine, and then you get an elimination reaction to form the alpha beta unsaturated ketone. Now, you can use pyridine. So in the second step, you can use pyridine, or you can use potassium T-butoxide, or you can use lithium carbonate. Now that is, I'm not sure if that's probably substrate dependent, meaning it depends on the ketone that you're starting with. But again, it's a scenario where you can use more than one type of base. And if you're wondering, what's the point behind making an alpha beta unsaturated ketone? Well, we're going to look at that, alpha beta unsaturated ketones in detail later on when we talk about a reaction called Michael addition. So that's something we're going to discuss in detail in the near future. Not today, but in the near future. Well, let me show you another reaction here. And this reaction is a really interesting mechanism that I don't think, or I'm not sure, but I don't think it's completely understood. And it's called the Hell-Volhard-Zelinsky reaction. It's a lot of last names, right? A lot of people getting some credit for this wonderful reaction. And we shorten that to the HVZ reaction, okay? Makes it a little easier to say. The Hell-Volhard-Zelinsky reaction is a necessary reaction because if I back up, I didn't tell you this, but this reaction, where is it? This reaction here, alpha halogenation, doesn't work on a carboxylic acid. So we could even write that in here. Why don't we just scribble that down? Will not work on a carboxylic acid. And so if we have a carboxylic acid, can we do alpha halogenation? The answer is yes. And to do that, we're going to use the HVZ or Hell-Volhard-Zelinsky reaction. So brominates at the alpha carbon of a carboxylic acid. This one's a little bit more involved, right? A little bit more to know here in terms of the reagents. First, you start with bromine, right? Molecular bromine, and PBr3, that's phosphorus tribromide. It's a covalent compound. I mean, you should know how to name covalent compounds, but hey, it's a Wednesday morning. So you treat it first with bromine and phosphorus tribromide, and then you end up forming the alpha bromo acid bromide, which is this here, and then you just hydrolyze that with water. So you throw water on it, and boom, it reacts and gives you the carboxylic acid. Now, again, you can't completely see here because of my margin, but again, what you're getting is you're ending up with the carboxylic acid. So you have your carboxyl, and you're adding a bromine here like that, the HVZ reaction. Now, the mechanism is believed to be the following sequence. So the first step is the reaction with phosphorus tribromide to give you the acid halide, or it's an acid bromide specifically in this case. That undergoes tautomerization to give you the acid halide enol. That's enough functional groups for you. And then that's going to react as a nucleophile to the bromine. And then finally, you hydrolyze it with water in the end. I'll be honest with you, I'm never going to ask you about this mechanism, right? It even says here it's believed to be the following sequence. Not going to ask you, and it he doesn't even have any curved arrows drawn in here, right? And so all you're responsible for really here is knowing the steps. First step is bromine, phosphorus tribromide. Second step is water, and that does alpha halogenation. And if you're wondering, well, come on, Mr. Guillaume, why does he do stuff like this? Like, why does, the most popular organic chemistry author in North America, why does he do stuff like this? Shows you a mechanism with no curved arrows. Well, I would say the reason why is because David Klein is very mechanism focused, and he really likes to break everything down into a mechanism, hoping that that's going to help you be able to rationalize what the heck is going on. Now, this is a case where there's no curved arrows, so it might not be as effective as some of the other mechanisms, but I think it still stands instead of just blindly memorizing the reaction. And again, there's no problem with that. Okay? If you want to just memorize the reagents, there's no problem with that whatsoever. In fact, when I learned that reaction, that's how I did it. Let's see here, alpha halogenation. Can we do alpha halogenation under basic conditions? Well, come on, it's organic chemistry. Of course we can, right? And this mechanism proceeds by a mechanism that proceeds exactly probably how you imagine it, right? First, you do deprotonation at the alpha carbon, right? We have, in this case, we have 2,2-dimethyl cyclohexanone. So we have acidic protons here. You're going to rip one of those off with your base, and it's going to act as a nucleophile. That's it. Okay? Nothing more than that. So you'd end up with what? Sodium bromide and water in your balanced equation at the end. So we could even write that in here, plus sodium bromide, which is a salt, plus water. Okay? So simple reaction, alpha halogenation under basic conditions. So treatment with sodium hydroxide and bromine in the same reaction pot. No steps to worry about. And there we have it, folks. So now we've learned alpha halogenation under acidic conditions, which is that autocatalytic reaction we looked at. Catalytic amount of acid and bromine. And then here we need a stoichiometric amount of the base when we do alpha halogenation under basic conditions. All right. Now, you might be wondering about this, and maybe not, but maybe yeah, maybe no. You think, okay, well, hold on, Mr. Dion. Isn't there still an alpha proton here? Yeah, there is. And let me tell you something, that if you look at these two alpha protons here, okay, if you compare the pK of these alpha protons to this alpha proton, could anybody make a guess, or an educated guess? Which one of these protons do you think is more acidic? The ones that are written in red, or the one that I have written in green at the bottom of the slide? Which one do you think would be more acidic? Yeah, it's the green one. Why would that be? Well, the reason why that's even more acidic is because not only do you have, the resonance stabilization of the conjugate base, but you've also got an electron withdrawing group, right? Bromine is an electron withdrawing atom. And so this is even more acidic. Okay? And so if you put in excess of sodium hydroxide, that reaction is going to be like the Energizer bunny. It's just going to keep going and going and going. And so it would do it again. So you end up with polyhalogenation. So we end up with two bromines here. Once the ketone is brominated, it forms an enolate and brominates again at an even faster rate because the alpha hydrogen is rendered even more acidic. Okay, so you end up with this intermediate, right, which is this guy. Okay, like that. And then that's going to react even faster. Okay, faster. So we'll put here fast and faster. All right, now you might be wondering, okay, well, what's the synthetic utility of that? Well, if you have a ketone that's not cyclic, if you have a methyl ketone, so if you have a methyl ketone, I shouldn't have said not cyclic because a methyl ketone, or if you have an ethyl ketone, it won't work. But if you have a methyl ketone, you've got 3 alpha protons here, right? You got 1 alpha proton, 2 alpha protons, and 3 alpha protons, like that. And so you can do that deprotonation and that bromination mechanism 3 times, right? So you're going to do the NaOH Br2 3 times. You're going to do that same damn mechanism over and over and over. And you're going to end up with this guy, okay, where you have 1, 2, 3 bromines in this case, and you have this tert-butyl over here, okay, like that. Now hold on. Now you've got, look, 1, 2, 3 electron withdrawing groups, 3 EWGs. Okay, that's a lot of EWGs. Okay, and so does it make sense that we could hydrolyze that in the end? I think so. Do I have the mechanism on the next slide? Yeah, I do. Okay, so we end up forming that compound with the 3 bromines, and I have the mechanism shown over here. I draw it in a couple of places. Anyhow, after all 3 alpha protons are replaced, the carbon with the 3 bromines acts as a good leaving group. Hey, that's something that we don't even think of in this class very often, right? We don't think of carbons with negative charges being good leaving groups, right? We don't think of this as being a leaving group, but in fact it is, right? Why would this be a good leaving group? Because the carbon has those 3 electron withdrawing bromines on it. And so in the last step, we can treat it with, well, it said acid on the last slide, so we'll fill in here. Why don't we write this in here? Or hydroxide, like that. So when we treat that intermediate with hydroxide, it comes in and acts as a nucleophile. And you're like, well, that looks like a nucleophilic acyl substitution to me, Mr. Dion, and you're absolutely right. Okay, but check this out. What's the driving force for this reaction? Because the CBr3 minus, right, that can act as a leaving group, but it's still not that hot of a leaving group or anything. What's the driving force? If you look at the first two steps of this mechanism, right, nucleophilic attack followed by loss of leaving group, okay? So we get our nucleophilic attack, our loss of leaving group. Those are both reversible. But hold on, you form this negatively charged carbon, okay? And that is going to deprotonate the acid to give you this compound, which is called bromoform. And that is, in fact, the driving force of the reaction, is that you end up with a resonance stabilized carboxylate. Okay? It says it right here. The resulting carboxylic acid is deprotonated under basic conditions, and that is what forces the reaction to actually go to completion. And there is a name for this reaction, which I hope is on the next slide. Do I have it here? No? Okay. Well, there is a name for this reaction. It's called the haloform reaction. I'd have to go back to the book to see if it's mentioned in there. Anyhow, the haloform reaction. And we can do this reaction using bromine, chlorine, or iodine. So if it's iodine, it would be the iodoform reaction, bromoform reaction, chloroform reaction. So it's a synthetically useful way to prepare carboxylic acids for methyl ketones. Come on, you guys. Think of all the crazy reactions that you learned with carboxylic acids back in chapter 20. Okay, so I'll refresh your memory that you spent a lot of time learning about carboxylic acid chemistry. So you can imagine that if this is something where we can take a methyl ketone and convert it to a carboxylic, this reaction is going to come up quite a bit in the practice problems. Okay, so this is a really important reaction. Treating a methyl ketone with sodium hydroxide and a halogen, bromine, chlorine, or iodine, and then hydrolyzing it. And again, it can be hydrolyzed with acid, and we'll write here, or hydroxide. Either way is going to work. And then they're going to ask you, what do you remember of carboxylic acids? Can you do this? Can you do that? Right? All kinds of stuff. So I've got a bunch of questions here to look at as a group, and I hope you took a look at these before coming to class today. And if you're just watching the video on YouTube, I would recommend, pausing the video after you read the question and giving it a try before just watching my explanation. 21.8 says, predict the major product for each or the following reaction and propose a mechanism for its formation. Well, in the interest of time, I'm just going to draw the intermediate that's formed here. Okay. First, we're going to end up forming the alpha bromo ketone after the first step. So after step 1, we're going to end up, so let me do it like this. We'll say after step 1, we're going to end up forming the alpha bromo like this. And then after the second step, when we treat that with pyridine, we're going to end up doing an elimination, and we're going to end up with the alpha bromo, the alpha beta unsaturated ketone. It's like, that didn't sound right coming out of my mouth. Okay, like that. Son of a gun. There we go. All right, let's move on to the next one. Identify the reagents that can be used to accomplish each of the following transformations. This is the question I wanted to get to today, is to look at some synthesis problems. I'll let you think about this one for a second. Well, the way I would do this synthesis is I would think about it in terms of retrosynthesis, right? So, no, actually, I wouldn't think of this in terms of retrosynthesis. I would think of, yeah, good. Sorry, I'm thinking out loud here. I would think, if I could get to this compound, if I could get to this alpha bromo ketone, right, then I can treat that with pyridine, okay, or lithium carbonate, or potassium T-butoxide, and I'll do the elimination. Okay, so either one of those will work. But the first thing I need to do is I'm going to have to oxidize that alcohol to a ketone in order to install the bromo in the alpha position. So who could choose some conditions for the oxidation of cyclohexanol to cyclohexanone? Let me draw a line here. So I want to oxidize this to cyclohexanone. Who's got an idea about that one? Sorry, let me go back to my chat here. Does anybody have an idea of what their favorite conditions might be, or can choose some conditions? So not for oxidation, not for oxidation. That's for the, so David, that would be for the installation, right, of the bromine. There we go. Adriana says, why don't we use Jones oxidation? So this is using sodium dichromate. Yes. Sulfuric acid and water. That works, right? Another one would be PCC or desmartin periodinane. Either one of those will work. And then David says, okay, well, next, why don't we treat that with a catalytic amount of acid and bromine, okay? And then we'll end up with this compound, right? Like this. And then when we treat that with a base like pyridine, okay, so I'll just write pyridine, the mechanism of that elimination is going to look something like this, right? Where you have this proton, and then the pyridine is going to come in as a base. So let me draw my pyridine molecule like this, like that. There we have it. And there we go. My pyridine can come in and remove that proton. And we'll do our elimination like that. And that gives us our alpha beta unsaturated ketone. There you have it, folks. Let's try the next one. Again, we're just looking for reagents to do this synthesis. Again, I could think of this one in terms of retrosynthesis and just say, okay, well, if I had this, you know, if I want to make this alpha beta unsaturated ketone, I'm going to want to have, at some point, I'll want to have this compound. Sorry, alpha beta unsaturated aldehyde. Jeepers. Mr. Dion, you need to wake up. All right. Yeah. And then we would want to treat that with pyridine, right? Potassium T-butoxide or lithium carbonate. We'll just write pyridine to keep things simple. And so, again, what's our first step going to be? We want to oxidize that to the aldehyde. And if we want to oxidize it to the aldehyde, we're going to have to use milder conditions like pyridinium chlorochromate in dichloromethane, and that would give us this compound. It looks like this. We'll draw the carbonyl pointing up like that. Then we're going to use the conditions for alpha halogenation, acid, catalytic amount of acid, and bromine, like that. That's going to give us this alpha bromo aldehyde. And then in the last step, we'll treat that with pyridine. Pyridine. Okie doke. Told you I had a lot of problems, a lot of questions here. 21.10, it's asking us to predict the major product of the following transformation. Okay. If we look at these conditions, bromine and phosphorus tribromide followed by water. If we back up in the slides, I just want to show you, where is it? Right here. This is what's known as the HVZ reaction, or the Hell-Volhard-Zielinski reaction. Let's go back. We're going to do an alpha halogenation on our carboxylic acid. Where the heck was it? Right here. So we're going to end up doing an alpha halogenation. Remember that the intermediate that's formed, and again, I'll never ask you to draw this intermediate, but if you're the kind of person that needs to know, like after every step, what the heck is happening, well, after the first step, you end up with this intermediate. You have the alpha bromo acid bromide in this case, and then you simply hydrolyze that with water in the second step, and you produce the alpha bromo carboxylic acid. So you can even use a condensed structure like that. There we go. So again, this is the HVZ reaction, the Hell-Volhard-Zielinski reaction. Another one that asks us to identify some reagents to accomplish each of the following transformations. You're going to need to use reactions from previous chapters. This sounds like something where we're going to need some more space. So why don't I grab a blank document here and we'll find a good spot to work. And so this is question 21.11 and this is question A. So we're starting with benzyl bromide, which is this compound. Okay, I'll just write the bromine like that. And then we want to do the HVZ reaction, right? If we want to make this compound. There we go. So the bromine and the carboxyl. So this is an alpha bromo carboxylic acid. Therefore, we're going to need the HVZ reaction. Now, in terms of retrosynthesis, that means that I would need to make this compound, or I need to have this compound. And so how do I get from benzyl bromide to this compound? You can see that I'm adding a carbon, right? Here I have a total of 7 carbons, and here I have a total of 8 carbons. And just in the interest of time, I'll show you probably the most effective way to do this, and that would be to use Grignard chemistry, right? If I treat this with magnesium and diethyl ether is merely the solvent in which the reaction is run. I would make this compound, this, benzyl Grignard, where I'd have this MgBr, right? But remember, we can think of that, get my pixel eraser, we can think of that as being a carbanion, like this, and having a positive charge. So if I want to add a carbon, if I treat that with carbon dioxide, CO2, right? This is CO2. Okay, well, what's going to happen? This is going to act as a nucleophile. The CO2 is a good electrophile, and I end up with a carboxylate. Okay, so I end up with this carboxylate where I have an extra carbon. Then all I have to do is treat that with acid, and I end up with the carboxylic acid, like this. And then the last step is going to be the HVZ reaction. What were the conditions for the HVZ reaction? So first step is to treat with bromine and phosphorus tribromide. And the second step is to put water on it. Okay, so this is the HVZ reaction. There you go, kind of a neat synthesis that employs some Grignard chemistry and some new chemistry that we've looked at today.